Hi everyone. Today we're continuing our discussion on orthogonality in the context of projections. When we talked about the fundamental theorem of linear algebra part 2, what we said was that the column space, the four fundamental subspaces of a matrix actually come in pairs of orthogonal complements. So if you recall, we had this picture here. This was the row space of a matrix. So let's say matrix A. So this was the row space of A in Rn. And it has an orthogonal complement, which is the null space of A. And using the matrix A, or multiplication by A, we saw that the row space gets transformed into the column space. And the orthogonal complement of the column space is the left null space of the matrix A. Now, today, this was in Rm. Today we're going to actually talk a little bit more about these two subspaces, and I'll explain the context. But the idea is that these subspaces, so the row space and the null space, this pair, and the column space and the left null space, well, these subspaces being orthogonal complements, what that means is that if I take an arbitrary vector, so if we take some vector b in Rm, so a vector with m components, we are not guaranteed that this vector m will be in the column space of A, unless the left null space is 0, right? So if this is just the 0 vector, then yes, everything is in the column space because the column space will be all of Rm. But if the column space is not all of Rm, so if we have a non-trivial left null space, then there will be vectors b which are not in the column space of A. And whenever we have vectors b that are not in the column space of A, then Ax equals b would not be solvable. So Ax equals b has a solution only if b is in the column space of A, right? But here's the key point. You can take any vector b in Rm. Because the column space of A and the left null space of A are orthogonal complements, what that means is that there will be, so if I take a b here, there will be a part in the column space and another part in the left null space. Of course, all of this discussion could have been done about the row space and the null space. The point here is that we have two subspaces which are orthogonal complements of each other. And what that means is that you can take any vector in Rm and represent it as a sum of a vector in the column space of A and another vector in the left null space of A. We will call this vector in the column space, this component of B, which is in the column space, will denote it by P, and we will denote by E the other part that is in the left null space, so that we actually have B equals P plus E, with P in the column space of A and E in the left null space of A. The key here is that Ax equal to P, so Ax equals P, except this would not be the same x, there would be an x hat, would always have a solution even if ax equals b doesn't. So you see, if you split the vector b into a part that is in the column space and the part that is not in the column space, so this is under the assumption that this split into a column space and a left null space is non-trivial, meaning you do actually have a non-zero left null space. And we take a vector b in Rm, which is not entirely contained in the column space. So if we take such a vector not entirely contained in the column space, then it will split into a part that is in the column space and another part that is not. And because that other part is not in the column space of A, it is in the left null space of A, or rather we are choosing it to be in the left null space of A. We also know that P and E are orthogonal, right? Or their dot product is 0. So this will be the idea for today and for tomorrow. So this is a very important application nowadays. We talk about machine learning, data science, all kinds of approximations. So I'll talk a little bit more about that tomorrow. This is actually a very, very useful part of the course that we're going to be studying about with very important applications. And the question for today really will be how to find that P. So today's problem how to find P. And why do I label it as P? Because this is what the projection, we will call this the projection of B onto the column space of A. So P, we will refer to P as the projection of B onto the column space of A. Okay, this is the big picture problem for today. Now, let's start with something simple. We have all seen projections. So whenever we talk about, when I want to represent something geometrically, I'll go as high as three-dimensional space, but the beauty of linear algebra is that you can extend that to any subspace. So the picture in 3D kind of extends naturally into higher dimensions. So let's say we have 3D space, maybe like this, and I want a line through it. So in order for that line to be a subspace, I'm going to take a line that goes through the origin. Okay, so this is some line. And this line, which is a subspace in R3, so this whole picture is in R3, but it doesn't have to be. The same idea works. I'm going to assume that this line is defined by some vector A. So I'm going to take some vector A on that line. So as long as it's not the zero, as long as it's not the origin, any vector A will do, in the sense that the line will just be the set of all multiples of A. So all multiples of A, we actually have a notation for this. That's span A. So you see any vector, you only need one vector because the line, a line is a one-dimensional subspace. So you know that if you want a basis to describe that subspace, one vector will do. Whether you take A or 2A or 3A or 5A, doesn't matter. One vector will do. Okay, now let's say I take another vector in 3 space, which is not on the line. So let's say I take this vector and I will call that vector B. B is not on the line. I'm interested in the orthogonal projection of B onto the line that contains A. So I'm not talking about the projection of B onto A. That doesn't make sense, a projection of one vector onto another vector. But what does make sense is the projection of B onto the line that contains A. I'm going to use another color here for the error. So this is how we project. You've seen this in calculus, high school, many times. So we project under an angle of 90 degrees. This over here is not part of the projection. We'll call that an E. And what is part of the projection is exactly this part. Now, the brown-orange thing, that's the projection P. And what we know is that the projection is on the line, therefore it is a multiple of A. So I'm going to write that as x hat A, where in this case, in this simple example, x hat is just a number, right? Because we just want a multiple of the vector A. So A is a vector, x is a number. Now, what about E? How do we find E? Well, if you recall, the way we add vectors, we have this vector plus this vector equals B. That's exactly how we add two vectors. In other words, the original vector B splits into two parts. The one part is the projection along A, and the other part is all that's left, which is actually the orthogonal component we also call error component. Why error? Well, if we were to use somehow, and we'll do that tomorrow, we will use the projection P in place of B in order to solve a system AX equals B. So instead of, whenever B is not in the column space of A, AX equals B does not have a solution. The closest thing to solving a system would be to say AX hat equals P, because P is going to be in the column space of A. The second system will have a solution which will only approximate the previous solution. So it will not solve it exactly, but it will approximate it. Again, we'll talk about that tomorrow. But the point is that this E, the error, the point of the error is it measures our mistake in using P instead of B. So that's why we label it an error term. So what we know about E is that E is equal to B minus P, right? So we have that error. And because E is orthogonal to A, we have a couple of equations here. I'm moving back to black pen. So we know that P is a multiple of A. We know that E is the difference between B and P. And we know that E is orthogonal to A, which means that, E dot product A is 0. So I can write that E dot A, or I can write it as E transpose A. And because I want A to be on the left-hand side. It doesn't matter, it's the same expression, or it means the same thing, but it will just look a little prettier. So I know that the dot product of A and E is 0 because the line A, or the line passing through A, is orthogonal to E. That's exactly how we chose E, which we can also write as A transpose E equals 0. And in fact, we will always sort of go towards that notation because it extends to matrices as well. So now from these expressions, from knowing what P is, or rather from the equations E equals B minus P and A transpose E equals 0, we would like to find what this x hat has to be, because that's how we will find the projection. So putting these two things together, I have A transpose times, instead of E, I'm going to have B minus, and instead of P, I'm going to have x hat A equals 0. Now, A and B are known things. We start with a vector B, we're trying to project onto a line that contains the vector A. So you take A and B as known quantities, and the goal is to find x. So if we open brackets here, we're going to have A transpose B minus, so when we're very careful about matrix multiplication, remember vectors are matrices, so the smart thing to do is just say A transpose x hat A. However, because x hat is a number, it can come up front. So actually, I want to write x hat A transpose A equals 0. Now, because we're dealing with vectors, A transpose B represents the dot product. It's just a number. So this is just a number. And this is just a number too. So what I can do, I can take things on either side. So what I have is A transpose B equals x hat A transpose A. And from here, dividing by A transpose A on both sides, which I can always do because, remember, if A is not 0, A transpose A is a positive number. And of course, if I take the 0 vector, it doesn't make sense to project onto it. So I'm assuming that A is not 0, and therefore I can divide by A transpose A. So what I get is that x hat equals A transpose B over A transpose A. So this number that defines precisely the projection of B onto the line containing A is given by that number, in the sense that P equals A transpose B over A transpose A times A. So you see here, what is in the parentheses is just a number that multiplies A. So we're getting a multiple of A. This is the projection. Now, yesterday, or even let's look at this picture here, I said when you apply A, when you do matrix multiplication, if you take a vector here, say x in the row space, and you apply A onto that vector in the row space, you're going to get a vector in the column space. You can also take a vector from the null space. So if we take a vector here, x in the null space, so xr is in the row space, xn is in the null space, and if we add those two vectors together, when we apply A to them, we get a vector in the column space of A. Well, how do we get that vector? Because we are multiplying by the matrix A. So you see this change from a space Rn into a space Rm happens via matrix multiplication. Well, in a similar way, in this picture here, we can take this vector B, which is not on this subspace. We can take that vector B, and when this idea of projecting can actually be represented via matrix multiplication by some projection matrix P. So how do we find that projection matrix? Actually, it's not difficult to see it from this very P that we have found. The only trick that we have to do is get this B to come over here, because what we want to do is we want to apply a matrix P onto the vector B to get its projection little p. So what can we do? Well, I could take this A and put it on the left here. And the reason I can do that is because A transpose B is nothing but a number. So I can take the number, put it here, and vice versa. So if I write P to equal A transpose B over A transpose A, I see my B sort of isolated on the right-hand side. And in fact, I can write this is perhaps the most elegant way of writing, 1 over A transpose A times A transpose, all of that applied onto B. Now, why did I write it like this? Because you see, A transpose is a matrix. You have a column times a row. A is a column, A transpose is a row. This is a rank 1 matrix. And that makes sense because we are taking this vector B and trying to project onto a one-dimensional subspace. So rank 1 will ensure that we are projecting exactly onto a one-dimensional subspace. So the matrix capital P, this over here, is the projection matrix. The reason I moved away from writing this as a fraction is because we normally don't divide matrices, but 1 over A transpose A is a number because A transpose A is the dot product of two vectors. Therefore, this will be just a number, and we would be multiplying that number times the matrix A to give us, which we will then, so this will be the projection matrix, which we apply on the vector B to get the projection little p. So the projection matrix, capital P now, is 1 over A transpose A times A transpose. Now, this is the matrix only in this one-dimensional case when we are trying to project onto a line. Now, I wrote here R3, but we didn't use the fact that B has 3 components absolutely anywhere. So if I were to remove the coordinate system here, everything stays the same and absolutely valid, as long as I have that identification that this is 0, because we said we would represent vectors as arrows starting from the origin to some coordinate. So as long as you have this representation, it really doesn't matter whether you're in 3 space or 5 space or 735 space. So this works in general. Now let's look at an example. So here's example 1. And the question will be to project the vector B equal to 1, 1, 1 onto A equal to 1, 2, 2 to find the projection P equal to x hat A. Now, I said it doesn't make sense to project one vector onto another. This is just a shorthand expression of saying really project B onto the line passing through A or onto the space generated or spanned by this vector A, which is the line passing through A. So it's a matter of applying the formulas. First, we have to find x hat, or we can go straight away into finding what the projection is. we actually have the formula conveniently. So that's this formula over here. Why not just copy it, I suppose. So the formula that we have is right here, and all that we have to do is apply that formula. Because I'm not asked to find a projection matrix, I don't have to rewrite that A and that B. So I need to find A transpose B first, or the dot product between A and B. That equals 1 times 1 plus 2 times 1 plus 2 times 1. That equals 5. A transpose A equals 1 squared plus 1 squared plus 1 squared. That equals 3. Oh, sorry, I took B instead of A. My bad. 1 squared plus 2 squared plus 2 squared. That equals 9. And so the projection P is simply 5/9 of A. Okay. Now, what if we wanted to add or to find the error term? So let's say part B here. Find the error term. Well, the error term E is simply B minus P. Therefore, it is the vector 1, 1, 1 minus 5/9 of the vector 1, 2, 2. Now, this may not be calculations that you like to do, but they're not that hard either. So think of 1 as 9/9. 9/9 minus 5 is 4/9. Then we have 9/9 minus 10/9. We have -1/9 and -1/9. And perhaps a lot nicer to write this as 1/9 of 4, -1, -1. So what do these E and P do? Let's remind ourselves. So we are here in this particular example in 3 space. The line passing through A is a one-dimensional subspace, and everything that all the error terms actually fill out a plane, which is the space orthogonal to the line A. So that plane that is orthogonal to the line. And what we have done is we have decomposed the vector B into a part along the line and a part along the plane. So if I were to draw that picture, let's see. So here is the plane, and somehow the line here, and this line is orthogonal. So this line contains the vector A. Somewhere here is A. And the error term E is somewhere on that plane. And then the sum of those two vectors is, sorry, not the sum of A and E, but the sum of P and A. So if that's A, 5/9 of it is somewhere here, for example. So this would be the projection P. And the sum of P and E gives us the vector B. So if we add those up somehow, I don't know, in 3 space how that will look, but that would be the vector B. So we did that decomposition into 2 orthogonal complements. You see the plane is the orthogonal complement of the line going through A within R3. Okay, that's enough for this video.